Hello everyone, welcome back to another SLHL IB chemistry video. Today we are doing part 3 of covalent bonding, so let's get right into it. So the element carbon can form different allotropes, or in other words, different structures with the same element, in this case, just carbon. And the four main ones that we need to know are fullerene, graphite, graphene, and finally diamond. So let's take a look at what these structures look like. So firstly, let's start with fullerene. As we can see here in this wonky circle, we can see that each carbon will be bonded to only 3 other carbons. Remember, carbon can form up to 4 covalent bonds. So this free valence electron permits this structure to be able to conduct electricity. And also, this fullerene structure, as we can see, is made of a series of hexagonal and pentagonal rings, creating this hollow sphere shape. But this can also come in either a tube or ellipsoid type shape. And because of its hollow structure, this will often be used in the medical field through drug delivery systems. And finally, if we just zoom back in to this circled area, we can see that these carbons show a trigonal planar molecular structure. Next up, we have diamond, which is yet another giant covalent structure. Each carbon here creates 4 covalent bonds with other carbons, meaning there are no free valence electrons. This means that this cannot conduct electricity, and the fact that it has 4 bonds, all in opposite directions, means that this is also a very hard substance. And another property of diamond is that it is transparent due to its purity and hence lack of impurities. And if we look at these carbons here, 1, 2, 3, 4, we see that we have tetrahedral structure. Next up, let's look at graphene. Now, graphene is presenting to us here a honeycomb type lattice with each carbon bonded on 2 covalently, 3 other carbons, creating this 2D sheet. As we said earlier, only 3 covalent bonds, so it is electrically conductive. And due to its 3 bonds to other carbons in this trigonal planar geometry, graphene ends up being a very strong molecule. And if we look at graphite here, graphite really is just many graphene layers which are stacked on top of each other. So graphite is another giant covalent structure which also conducts electricity, but this one is brittle and slippery. And this is because, as you can see by these dotted lines shown between the layers, we have intermolecular forces acting between our graphene sheets which hold them together. But these forces tend to be fairly weak, making it very easy for them to slide over each other and repel. Next up, we have to know about silicon and silicon dioxide. So, silicon is an element in the periodic table, which often occurs in a giant covalent. That's not right. Silicon dioxide presents a giant covalent structure. Let's get an image of that right now. So here we have what silicon dioxide looks like, and as we can see, each silicon is covalently bonded to 3 other oxygens and 1 other silicon atom. It creates a tetrahedral structure. Now, silicon dioxide is but brittle. Now, in terms of silicon and silicon dioxide, these both create giant covalent structures which are very hard and brittle. They both have very high melting and boiling points, and their molecular geometries are also tetrahedral. And let's just insert an image to demonstrate what these would look like. So this here is what silicon dioxide would look like. As we can see, we have our tetrahedral structure, just that between our silicons we have oxygen atoms, and this would be the same for silicon, except that we would just remove these oxygen atoms over here. In terms of comparing silicon to silicon and carbon to carbon bonds, so our carbon allotropes have a shorter bond length with a greater effective nuclear charge than silicon. So this means that these bonds, carbon-carbon bonds, will be stronger than silicon-silicon bonds. So generally, your carbon allotropes will be stronger, having higher melting and boiling points than silicon and silicon dioxide. Next up, let's take a look at intermolecular forces. All intermolecular forces come under the umbrella term of van der Waals forces, and these can be broken down into three separate components. So your first type of force is a London force. In these, you will have electrons which are free to move within a bond. For example, you will have two chlorines, just like this, and they share their bond a little bit neater than that, and they will have their electrons. Now, a London force is an instantaneous, induced, or temporary dipole. Now, how this happens is that essentially these electrons may, for a very split second, not even a second, a much shorter quantity of time, all be closer to chlorine 2 than chlorine 1. And this will make chlorine 2 slightly more electronegative than our chlorine 1, which will induce an overall charge on this bond. These instantaneously or temporary dipoles can be induced in neighboring molecules. So say if we had another chlorine over here, the electronegativity over here could pull the electrons to that side of the bond over there, as they are quite close to each other, and this is a instantaneously polar molecule. In terms of London forces, the heavier the molecule, the stronger the London force will be, and that is due to the increased nuclear charge drawing electrons more strongly towards itself. And London forces occur in all simple molecular compounds. And in terms of their bond strength, these are the weakest at about 1/100th of a covalent bond. Next up, we have our dipole-dipole. So dipole-dipole. Now, our dipole-dipole bonds, or permanent dipoles, only occur in polar molecules, such as ammonia over here. Because here we will have a permanently more electronegative region here near our lone pair in comparison to our more electronegative at our nitrogen and less electronegative at our hydrogens. So these have about the strength of 1/20th of a covalent bond, and here partially charged ends can attract and repel, or as we said earlier, react with other compounds, And do keep in mind that even if you do have a dipole-dipole force, your London forces will always be acting, because as we said, every single molecular compound has a London force. And finally, we have our hydrogen bonding. So hydrogen bonds occur when you have hydrogen with one of the three most electronegative elements on the periodic table, being oxygen, nitrogen, or fluorine. These are the strongest intermolecular forces, as there are no electrons to repel in this pair. And this is essentially a special kind of dipole-dipole because, as we said, it only occurs between hydrogen and one of these three elements. This is the reason why, for example, water freezes down, meaning that when it freezes, its structure as a solid is less dense than a liquid, because as they solidify into place, let's draw this out, we will have a more spaced out structure, leading to an increased volume in comparison to water in a liquid form, which can simply move around more freely. And finally, let's just look at some general rules of thumb in terms of the physical properties of molecular covalent structures. So these typically have low melting and boiling points, as little energy is needed to break the weak van der Waals forces between the molecules, because as we said earlier, these only have a fraction of the strength that covalent bonds actually do. These typically do not conduct electricity because molecules tend to be neutral without charged particles, as in ions or electrons, moving around and carrying charge, even though we have spoken earlier about our different carbon allotropes which can. And typically, covalent structures are also insoluble in water, except hydrogen chloride and ammonia. These are exceptions because they can react with water. That is all for today. Hope that this was helpful and that you enjoyed.